Now, let's do something more interesting. Something interesting meaning let's actually try to control at least some temperatures, for example, the temperature of the heating element in my water bath using a piece of controller software. Before we actually modify our controller class to do something useful, let's have a look at the big picture. And disclaimer at this point, this video is not intended as a tutorial or introduction to controlling theory, okay? With that said, we have our process, that is our laboratory water bath. In controlling theory, this is also sometimes called a plant, for obvious reasons. And it consists of our stainless steel bath with a temperature sensor connected to it, and our heating element with the temperature sensor connected to it, and we have our external temperature sensor, which is currently just dangling in the air. And we get these three temperatures out of our process, and these are called the process variables, and in controlling theory they are always called Y. Okay, so we have Y heater, Y bath, and Y external. And these are always function over time. This is basically a function, that changes over time. For the heater temperature, the bath temperature, and the external temperature. We have a control variable, and they are always called U. In my case, I called it U heater because it's the heater on off. And that's also a function over time because, we can switch it on and off over time. And then we have our what's called a set point, and in control theory they use an R for set points, so I just called mine R set. Function of t again, because our set point might also change over time. And our controller now gets all process variables, and it gets the set points and takes that information to switch on and off the heating element. That's a bit much if I want to keep this video below 2 hours, I guess. So keeping that picture in the back of our minds, let's try something simpler first. And build a controller just for the heating element, okay? So we just look at the temperature of the heating element, and our controller will give it an on-off signal. And the controller I want to use or try first is a so-called bang-bang or 2-point or on-off or hysteresis controller. And if you look at the picture, it very much looks like a Schmidt trigger, and that's basically what it is. So our Y heater, our heater temperature, is subtracted from our set temperature, and that gives us, we haven't seen that in the other picture, a error value, E, over changing over time, of course. And what such an on-off controller does is, if the error value is bigger than an hysteresis on value, it switches on. And if the error value goes back again and reaches a hysteresis off value, it switches off. That's simple. So if we look at the code changes in our controller class, there's not much. I now have actually a variable heater on boolean, and I initialize that with false in the constructor, so the heater should be off. And the other change is, of course, in our update method, which now gets the set temperature and the heater temperature. And I have these two hysteresis variables here, or constants. So on at 1.0 degrees Celsius error, that is if my heating element is 1 degree too cold, and off 0.0, that is when my heating element is actually at exactly the set temperature. I have the error value, yeah, we saw that in the picture. That's simply the set temperature minus the heater temperature. So this is greater than 0 when the heater is too cold and smaller than 0 when the heater is too hot. So, and if we are in an update, yeah, the update counter, that's still all unchanged. The error value is the set temperature minus the heater temperature, and if the error value is greater than the hysteresis on, yeah, we are too cold, at least 1 degree Celsius, we switch the heater on. And if the error value is smaller than the hysteresis off, yeah, 0 degrees, so we are exactly on, we switch the heater off. And yeah, of course, I return that here when I query heater on. No longer a constant true here, but really returning that Boolean value. And I think the changes in the main loop are, yeah, minuscule. I just pass the set temperature and the heater temperature to the controller update. That's it. Now let's see what that does. Okay, let's try that. I have the serial monitor, that is the serial plotter of the Arduino running too. And let's say we want to heat the element up. It's currently at 33 degrees to 35. And you see the blue line is my set temperature, and yeah, we have here an overshoot. And we do have a considerable overshoot, but you see the lilac line, that was when the heater was on. You see the heater was on, and we basically had absolutely no reaction, and then the temperature rose. And now, yeah, it's still rising and rising and rising. Well, that's not really good, is it? But to be honest, that was to be expected. I think we will have to wait quite a while until we are back down again, but yeah, that overshoot will be the... Oh, we are already going down again. Very slowly. But that overshoot that you see here, and yeah, you can see my mouse. So yeah, that was me adjusting the blue line, the set temperature to 25 degrees. And then I switched here the heater, enabled the heater, and yeah, the lilac line, the heater was switched on by the controller, and nothing happened for quite a while. And then the temperature rose, yeah, until we reached my set temperature, which is okay, and then we switched off the heating element, that is, the controller switched it off, but the temperature kept rising and rising and rising and rising. And now it's slowly and steadily falling. I don't think we have to watch that in its entirety. Let me set up the next experiment. Okay, let's try this again. It's the next morning. Things have cooled down again, and yeah, we're going currently through a heat wave here at the time of the recording. And start at 28 degrees. And again, I say my target temperature is 35 degrees and go. Oh, sorry. I have to switch it on too. Go. And we see nothing happens, nothing happens. And now the temperature is rising. And we crossed 35 degrees and it continues to rise. I'm actually expecting the overshoot to be a wee bit higher this time. We'll see. And we plateaued out and now things are cooling down again. Okay, I will let that run a while. And yeah, we make some more experiments. So my heating element is obviously cooling down again very slowly. And yeah, we are approaching my 35 degrees set temperature. So we expect it to switch on again at about 34 degrees. Yeah. So yeah, we'll see. We'll see, maybe the overshoot in the second cycle is not as bad. And yeah, 33.9, we are now below our hysteresis, and the heater came on. And temperature is rising again, of course, and let's see. And we plateaued out, and yeah, it's cooling down again. I will stop the video here at that point, and then we do at least 2 more other experiments. Up to now, our water bath was dry, and yeah, the external sensor was just hanging there in the air. But now let's put in a liter or 1,000 grams or 1 kilogram of water just as a thermal buffer and see if, yeah, we can put the sensor in too. Let's just see if things are different now. Okay, our goal should be, 35 degrees, and here we go. So, heater came on and heater stays on for quite a while, and heater is off. So yeah, business as usual. But we are already going down again. I mean, don't get me wrong. Yeah, this is my 35 degree line here. That is 40 degrees, and this is, yeah, somewhere above 45 degrees. So we still overshoot our temperature goal by 45 degrees. But yeah, I think we will see in this example, and now we're leveling out here for some reason, and now it's going down again. There was probably a sensor mishap in between. Yeah, I still have these sensor mishaps. I was fumbling around a little bit and thought I could make it even better, but I made it worse, of course. And now, any second, our heater should come on again. We need to be below 34.3, 34.1, 34.0, and heater. Wow. So basically what we have managed here with the water in is to capture here with one picture 2 cycles, which were the last 2 experiments we did, with just a much longer time constant. So the water is doing something. And I would love if we could capture just, the next crossing with my 35 degrees set temperature. This is, by the way, which sensor is that? That's the water sensor, directly above the heating element. It's almost touching. Yeah, we can ignore that for now. And the heater is coming on again, just for a very short time. And I think I can pull the plug now. Okay. Wonderful. A simple bang controller obviously doesn't work for that application, and to be honest, I didn't expect it to, because remember, I'm bang controlling, with a cord switch, my prototype of the laboratory water bath now for quite a while, every time I was etching a PCB. However, we learned quite a lot about the behavior of our system. Looking at the data of our first run, the initial thing we noticed is that for approximately 5 seconds after the heater switched on, nothing happened with the temperature of our heating element, or better, the sensor attached to our heating element. And only after 5 seconds, the temperature of that sensor started to rise. And it reached our set temperature of 35 degrees at 5 seconds later. So in total, the heater was on for 10 seconds. But then the temperature kept rising and rising and rising and rising and rising for total time. From the start, it started to rise until it reached the peak about 60 seconds, and we increased the temperature of the sensor by 29 degrees C. In control theory, they call these first 5 seconds, after you changed your control variable, my heater goes from off to on, and nothing really happens in your process variable, that is the temperature of my heater sensor, dead time, TD. They also define a time constant tau. So after your dead time, when your process variable starts to change and it reaches at some point, equilibrium again, stays constant. So you have a total change of your process variable, our temperature, in response to a change of the control variable, our heating element being switched on. And if you take the point in time where you reached 63%, or to be constant, 1 minus 1 over E of that total change, and measure the time when your dead time ended, that's your time constant tau. And if you ever worked with RC elements, you already know tau, because tau in electronics, or for our C elements, is equal R times C. And it's the time when you apply to an RC element a sudden change in voltage until you see 63% of that change of voltage at the output. And then usually after, rule of thumb, 5 tau, you see at the output the complete change of voltage. We certainly have a dead time in our system, but I'm a wee bit ambivalent, about tau, because, our control variable is, changing value again, going back to off long before we reach the top here. And so I'm just calling these 60 seconds from the end of the dead time until we reach, our maximum value, the time until we reach our maximum temperature. And if there are some controlling theory enthusiasts out there, I'm looking forward to your feedback on terminology in that case. Anyway, let's have a look at the other runs. On the second run, we got again a dead time of 5 seconds, and again it took about 60 seconds until we reached the maximum temperature. And this time we increased the temperature by 38 degrees C, and our heating element was on for about 14 seconds. On the third run, again, dead time 5 seconds. Again, approximately, time until we reach maximum 60 seconds, maybe a wee bit shorter, 58, 55 seconds, but order of magnitude 60 seconds. Delta of temperature 24.5 degrees C, and our heating element was on for 8.5 seconds. If you look at the numbers of the first 3 runs, you can already see a pattern emerging. So the dead time was always 5 seconds, so that's obviously constant, independent from our starting temperature. The time until we reached the max temperature was also about 60 seconds every time. So in the third run it was a little bit shorter maybe, but it's almost constant. So tau question mark. Obviously our heater on times were different, as were our delta t's. So, but if we divide our delta t by the time the heater was on, we get these numbers. So first run, 2.9 degrees Celsius temperature rise for each second the heater was on. Second run, 2.7 degrees Celsius per second. Third run, 2.9 degrees Celsius per second. And that is pretty much constant. Looking at the data from our 2 wet runs, with 1 liter of water in our water bath, we see very similar curves, but the numbers are a little bit different. Dead time is again, both times 5 seconds, but time to maximum is 23, respectively 21 seconds. And for 13 seconds of heater on, we get a temperature rise of 16 degrees. And for 9 seconds heater on, we get a temperature rise of 11 degrees Celsius. Putting the numbers also in our table and just looking here at the temperature change for seconds heater on, we get for the first one wet 1.5 Celsius per second, and for the second one 1.2 Celsius per second. So also aboutish constant. Of course, that changed between wet and dry runs. also the time to max, or time constant, also changed between wet and dry runs. But what's also absolutely constant is our dead time. Okay, it doesn't matter if we run that thing dry or if we run it wet. So, what can we learn from all that? And I have to make 2 points, and it will involve a little bit of math. So, first, our system has a thermal capacity, usually denominated as big C, and that's given in joules per Kelvin. And that's simply a measure for how much energy you have to put into a system to raise the temperature a certain amount. And the thermal capacity of our system obviously consists of the thermal capacity of the dry components, the metal, aluminium, stainless steel, whatever, plus the thermal capacity of the water we put in or we have in. And that, of course, changes over time. And the temperature change for such a system is given as the energy we put in joules over the thermal capacity. And if you work with capacitors, you already know that formula. So the voltage across a capacitor is equals to the charge you put into a capacitor over the capacity of a capacitor. It's physics. It's always the same. Now, the thermal energy Q we put into our system, given in joules, comes, of course, from our heater, or the heating elements in our heater. And fortunately for us who mostly dabble in electronics, 1 joule is 1 watt seconds. Not kilowatt hours, but watt seconds. And so the Q we put into our system is the power of our heater in watts times the time our heater was on in seconds. That's it. Of course, we have some thermal losses to the environment. The temperature is, or the energy is slowly bleeding away. We saw that as the system cooled down very slowly. Again, the analogy to our capacitor. Our electric charge Q is equal the current I times the time T the current flows. So I, our power, and T, our T. Now, in the end, we measured and calculated that delta temperature, so delta big T, over the time the heater was on. And if we now put all that math to it, we see that delta T over T heater on is equal to, delta T, the energy we put into the system divided by the thermal capacity over our time the heater was on, and our energy we put in is equal to the power of our heater times the time the heater was on over our thermal capacity divided by the time the heater was on. And we can drop that, and this leaves us just with the thing we measured is really the power of the heater over the thermal capacity of the system. So basically, in other terms, automotive terms, horsepower per pound vehicle weight, or more scientifically, kilowatts motor power over kilograms vehicle weight. So the power to weight ratio. Now, that explained nicely how our temperature change, our total temperature change, relates to the heater on time. But what about, the development of the temperature over time? To explain that, let's go back for a second to this overview picture from the beginning, where we have our process and the control variable, heater on off, goes in, and we're currently just using one of the process variables, the heater temperature, coming out. And I refined the process picture a little bit because in reality our heating elements are really just two tiny bundles of wires or something that are embedded in a block of aluminium, and that's where we generate the heat. That's what's really heating up. And everything around it, the stainless steel bath, the water, the aluminium itself, that's all thermal mass. And in the end, we are measuring the temperature of that aluminium here, not of the heating elements themselves. And keeping that picture in mind, more math. But I did my best to keep differential equations out of the equation. So we have our heating elements, okay, and they have a thermal capacity CHE for heating element. And you already know the formula, so the temperature change of these heating elements is equal to, what energy goes in the heating elements and what energy goes out the heating elements over their thermal capacity. And then we have the rest of the laboratory water bath, all the metal, the water, the aluminium. And same formula, so the temperature change of the rest of our water bath, and our sensor is connected here, that's the process variable we are really measuring, is the same, energy going in minus energy going out, we're losing some energy at some point, over the thermal capacity of that whole shebang. Now, how fast is energy flowing from the heating element into the rest of our system? And that's basically proportional to the temperature differential between our heating element and the rest. The greater the temperature difference, the higher the energy flow. Or if you ever calculated heat sinks, the energy flow is basically the temperature differential divided by the thermal resistance between the two. And of course, that is also true for the losses that flow out. That's the temperature of our rest minus the temperature of the environment, so the air around it, over the thermal resistance, that we have between our complete laboratory water bath and the environment. Now, how fast is energy going into our heating element? Well, that's pretty constant because our heating elements, they have a certain power, 200 or 300 watts, something around that. And that's going in here for the time we have the heater on. With that model, we can explain how our process variable, the temperature we are measuring, develops over time. And please note the curves I scribbled down here, they are not to scale and probably not mathematically correct, okay? But just as a visual aid. So when we turn on the heater for a few seconds, the temperature of the heating element is first rising very steep and then a little less steeper, because in the very beginning we have the same temperature here and here. So no energy is flowing from the heating element into the rest. But as the heating element is heating up, as we have the heater on, energy starts to flow, more and more energy, until we switch the heater off again. And then the energy flow, reduces itself slowly over time, because, the temperature differential between the two becomes less and less as the heating element cools again and the rest is heating up. And at some point, we have equilibrium again. So the energy flow between the heating element and the rest behaves quite similar. So at the beginning we have no energy flow, and that is rising as the temperature differential is rising, and then it's going slowly down again as the temperature differential is going back to zero. And in effect, we get the temperature curve for the rest. So starting slowly, then going to a maximum, and then flattening out again until we reach our equilibrium again. I've drawn in one of our measurements the temperature of the heating elements in red, and I traced the temperature of our rest in green just to give you a feel of the scale. So when we turn our heating element on, the temperature of the heating element shoots up, and it probably peaks somewhere off the screen at a few hundred degrees Celsius, and then as energy is exchanged, they come together again until they are in an equilibrium, and then everything cools down again. We lose energy to the environment. And we can have such high temperatures in our heating element, resulting in only 20-30 degrees temperature increase in our rest, because the thermal capacity of our heating elements is of course much smaller than the temperature capacity of the rest. Two closing notes. First, this is just a model of the thing, and it's not reality, and it's probably in certain aspects wrong. For example, I haven't modeled the lag time at all. Second, in controlling theory, this is called a second order system, because you have two energy stores in your system that communicate or that exchange energies. And if we would draw that as an electronic circuit, as you're familiar with, our electrical power heating up the heating element, that would be a constant current source which we can switch on and off, and that would charge a first capacitor. And that capacitor, charged for to a few hundred volts, would slowly charge the other capacitor, which would be much larger, to a obviously much lower voltage. And in addition, we have, of course, our losses here to the environment. Well, that was quite a lot to digest, but now we know what attributes our controller for the heater must have. I mean, first of all, it must be a predictive controller or model-based controller. So we can really know when we have to shut off the heater to reach a certain temperature. And fortunately enough, our model, just to predict the total temperature change, don't care about how, in which curve it's reached, is quite simple. All we need to know is that delta T over T heater on variable, or the thermal capacity of our whole system. And that leads us to our second point. Our controller must be self-optimizing/learning. It must, while it's running on the run, determine what's the delta temp per time heater on is, or the thermal capacity of the system, because you never know how much water or if any water is in it. And maybe, but that's totally optional, we can also learn about the time constant of our system. But as I said, I'm not really sure if that's a time constant in the classical sense. But that's definitely something for the next chapter in the software book of my laboratory water bath saga. Till then, bye!